In this lecture, we consider life at the extreme. The extremes of life on Earth are illustrative for astrobiology, or life beyond the Earth, because we need to know the full range of physical and chemical conditions under which biology can operate on this planet as at least a guide to what biology might be capable of beyond the Earth. But we should remember in doing this that that's just a bound provided by this planet. Physical conditions on exoplanets will be different, beyond the bounds of life on Earth, and life may well adapt to those increased boundaries or different physical conditions. So understanding the range of life on Earth is innately conservative because we don't know how strange life can be in other locations. But it's clear evidence now as we study the history of life on Earth that many of life's most important features and most successful components involve dealing with extremes of physical conditions. And so the idea of Darwin that life started in a warm little pond at a temperate process is probably not true. Life almost certainly started in deep-sea hydrothermal vents with high pressurized conditions and what would be presently toxic chemical conditions, and without even the sun's radiation penetrating. And even on the present Earth, we can find examples of life that likes extreme conditions, and these are called collectively extremophiles. Most biological life has evolved into recognizable forms that need sunlight, air, and water. But extremophiles are a class of organisms unto themselves. They have been found to inhabit environments on the Earth that will be uninhabitable to other forms of life. Extremophiles are generally, but not exclusively, microbial or bacterial. We'll give some examples of the ranges of conditions that extremophiles can function in. And when we say tolerate or survive, that's actually not quite right. Extremophiles thrive, persist, and do quite well with these extreme environments. There's no problem for an extremophile in their physical conditions because they've adapted through biology to those conditions. Extremophiles that can handle extreme cold are called psychrophiles or cryophiles, and they can survive temperatures below the freezing point of water. Now that's interesting because we've already defined habitable zone in astrobiology as the range of distances from a star where water will be liquid on the surface of an Earth-like planet. But we already have examples on the Earth of life that can persist in temperatures below the freezing point of water. Part of that's because of the unusual property of water as a molecule, which is when it freezes, it expands. Now, when water freezes, it would normally burst and kill a normal cell, disrupting the cell wall. So psychrophiles have evolved a type of biological antifreeze that prevents them from individually freezing as water freezes and expands. The other attribute of water that helps the persistence of life in cold environments is this same expansion property, which means that a large body of water will never freeze solid, but will have an icy top and never freeze all the way through, and so can average out extremes of temperature fluctuation to maintain a liquid part. Psychrophiles have invented, by natural selection, what amounts to antifreeze to survive below the freezing point of water. At the other extreme, the habitable zone stops at the point where water will boil, 100 degrees Kelvin. Normally, organisms begin to experience bad side effects at extremely high temperatures. Humans can obviously not withstand very high temperatures, so higher organisms are unable to handle extreme heat. But microbial organisms can handle heat, and they can handle temperatures beyond the boiling point of water. I think the current record is about 145 degrees C, substantially above the boiling point of water. Thermophiles, as they're called, tend to be found near hydrothermal vents and deep underground, where there's a lot of energy created from the interior of the Earth's core by radioactive heating. Now, this process cannot go on at impossibly high temperatures. There's a temperature beyond which DNA, the information storage molecule, or RNA, starts to unravel or denature. And so biology is not possible at certainly very high temperatures because the information storage essential to biology is not possible. Life has evolved in some situations an extraordinary capacity to withstand radiation. We talked about the buffering effects of the Earth's atmosphere and the Earth's magnetic field in protecting life from radiation from space. But some microorganisms, some extremophiles, tolerate and thrive with extraordinary high radiation doses. An extraordinary microbe called Dinococcus Radiodurans was discovered a few decades ago. These microbes were found actually in a can of meat that had been irradiated in an attempt to sterilize it. Subsequent study showed that they can tolerate tens of thousands of times the level of radiation that would kill a human in seconds. To do this, they have an extraordinary strategy. They actually have short fragments of DNA, and they keep stacked multiple copies of this DNA. They have a repair rate for their DNA, which all organisms have, thousands of times faster and more efficient than the repair mechanisms that humans use for their DNA. So these organisms, again, do not just tolerate, but they thrive situations of high radiation. Other microbes like this have been found too. So microbes have been found in situations of unusual radiation. There were microbes launched into the vacuum of space on the legs of spacecraft that apparently survived those situations for days. Another type of extremophile can handle toxic or chemically challenging environments. Most organisms, like humans, cannot tolerate heavy metals, and toxic mining sites, such as the EPA sites in the United States, keep humans away because these are so dangerous to humans. But in these same toxic sites, microbiologists found organisms happily living in the superheated water emerging from hot springs that was dissolved with high amounts of lead, cadmium, and other heavy metals like mercury. Extraordinary. In fact, these microbes were actually metabolizing these metals. Acidophiles thrive in regions where the pH is 3 or lower. And remember that tooth enamel dissolves at a pH of less than about 5. So we have tolerant organisms at all ranges of the pH spectrum, from battery acid to drain cleaner, and extremely high concentrations of toxic heavy elements. Once again, life on Earth has proved extraordinarily adaptable. Life needs water, but how absolute is that statement? There's a type of extremophile called a xerophile that have found their way into the popular media because of spectacular situations where life apparently survives extremely arid situations. Parts of the northern Atacama Desert in Chile are as dry as any place on the Earth. There are places there where it hasn't rained for over a century or in recorded history. And yet in these driest places on the Earth, where there's a tiny amount of rain and it's very episodic, microbes have been found. In fact, astrobiologists use these environments to train for Mars missions, because Mars is also a very arid place. And microbes somehow manage to find a way to persist in these environments. And they do so by taking their metabolism down to an extremely low rate. Their replication rate of their cells may be tens, hundreds, or even thousands of times less than the replication rate of plants and animals. Once again, they're also dealing with fairly high doses of radiation. So while life does need water, it doesn't need much water at all. And so we can imagine life in other situations in the universe where there's not much water present, or water is only episodically present. Exobiology is the idea of life beyond the Earth. And so we use the full range of life on Earth, especially the early Earth, where conditions were extreme, to understand what the range of life beyond Earth might be. And when we notice that life on Earth, extremophiles, has expanded into almost every imaginable niche in ecological terms, and some that are essentially unimaginable, then we've learned something important about the possibilities for life in the universe. Most of these extremophiles are not like us. They're single-celled organisms, very like the first life forms on the Earth. So how often does this form of life arise on other planets? The experiment of how life forms, other than looking in the historical record, can be done in the lab. And looking at the range of physical conditions for that life can also be done in the lab. The prototype of that experiment was called the Miller-Urey experiment. In the early 1950s, scientists Stanley Miller and Harold Urey carried out an experiment that was a classic study in what's called a biogenesis, the formation of life in the lab in a chemically controlled situation. Their apparatus, illustrated here on the left, sealed water, methane, ammonia, and hydrogen in a flask. These chemicals were chosen to represent the chemicals present on the early Earth and in its atmosphere. The water was boiled and energy was added, in this case by an electrical discharge. But in other versions of the experiment, it's done by ultraviolet radiation, such as might happen with lightning discharge. The steam rose after the water was boiled and passed through another flask with electrodes where the energy was added. And then the deposits that were left behind in the flask were studied over a period of time. After 1 week of running this experiment continuously, a brown sludge had accumulated in the U-trap and in the bottom of the flask. The sludge was analyzed to show that 5 of the basic amino acids necessary for life had been synthesized from the original simple ingredients. Further studies showed that this method of synthesizing amino acids on the early Earth actually generated a much larger suite of amino acids, nearly identical to those present in the Murchison meteorite, for example. And the grid of these is shown on the right. In fact, some of the original milliuri data was reanalyzed less than 5 years ago, 50 years after the original experiment, and more complex chemicals were found from their original data. The Miller-Urey experiment was wrong in one important aspect. It had too much hydrogen in the gas present in the flask, representing a reducing atmosphere. It's now thought that the early Earth released most of its hydrogen into space, so there was very little hydrogen in the early Earth's atmosphere. So people have redone the Miller-Urey experiment with atmosphere that more closely represents the early Earth's atmosphere, and the results are the same. Amino acids, other simple fats and lipids form naturally, without any special intervention, fairly quickly with the addition of energy. These life-in-a-bottle experiments from the 1950s and their more recent versions have not created life. None of them actually came even close. But they showed how plausible it is in the early Earth condition to generate from the very simplest chemical ingredients of just a few atoms in a molecule to more complex chemical ingredients with a few dozens of atoms in a molecule. And these are now molecules which have functional forms and shapes which facilitate further chemical reactions. Complexity builds on complexity, and that's how life must have started. And these other recent experiments alluded to just now say that vesicles or simple cell precursors could have formed and then concentrated these simple chemicals. So chemical complexity builds on itself in a positive feedback sense, and that's how it's conceivable that you can go from simple molecules of a few dozen atoms to the RNA and DNA chains millions of atoms long. And of course, all of this is in the context of what happens elsewhere. When a planetary system forms around a star with some habitable planets defined by their basic properties, how often will life develop on those planets? If we can't get life from the Miller-Urey experiment, but life formed on the early Earth when conditions were very extreme, how many of the exobiology situations we found with thousands of exoplanets are suitable for life? Planets are likely to be very simple in their overall chemical composition and quite similar to each other, with relatively large amounts of hydrogen, carbon, nitrogen, and oxygen, with phosphorus, which we know to be essential for ATP, the energy storing molecule, and have many of the same organic compounds present on the primordial Earth. We might say that our solar system started with 2 potentially habitable planets, and possibly 3 if we include a temperate early Venus. Life developed on one of those planets, and so do we know whether life ever evolved on Venus and Mars, making possibly 3 habitable planets over the whole history of the solar system? Our data is limited to the Earth. So in terms of trying to project these numbers out into space, we have to define a parameter to represent the likelihood that life will emerge given all the ingredients on a habitable planet. In our solar system, we might estimate that parameter as a half if we include Mars as a habitable planet, or maybe a similar number if Venus was also. When considering planetary systems in general, we really don't know how to choose this parameter. We could say that this fraction is 0.01, which means that life develops only on 1 of every 100 habitable planets, or 1, which means that every time the ingredients are there, given sufficient time, life evolves. This is currently the biggest uncertainty in astrobiology, And we can see how tantalizing the early evidence of the Earth is in considering this out in the universe. Extremophiles are simple organisms that expand the parameters for life, because they show that simple biological life forms present on the early Earth, and some of them still present on the Earth, can live in physical conditions that would be intolerable to complex forms of life like plants, animals, and us. Extremophiles are probably our best examples for understanding how life might adapt or evolve in the first place on exoplanets with similarly severe conditions. We've had experiments in the lab, like the Miller-Urey experiment, that show how the building blocks of life at the level of amino acids, fats, and simple bases can form quite naturally in concentrated solution simply with the addition of energy.